There are over 1 billion cars in the world today, getting people where they need to go. But cars aren't just a mode of transportation. They're also a chemistry lesson waiting to be taught. The process of starting your car begins in the engine cylinders, where a spritz of gasoline from the fuel injector and a gulp of air from the intake valve mix together before being ignited by a spark, forming gases that expand and push the piston. But combustion is an exothermic reaction, meaning it releases heat, lots of it. And while much of this heat escapes through the tailpipe, the heat that remains in the engine block needs to be absorbed, transported, and dissipated to protect the metal components from deforming or even melting. This is where the cooling system comes in. A liquid gets circulated throughout the engine, but what kind of liquid can absorb all that heat? Water may seem like an obvious first choice. After all, its specific heat, the amount of energy required to raise the temperature of a given amount by 1 degree Celsius, is higher than that of any other common substance, and we have a lot of heat energy to absorb. But using water could get us into deep trouble. For one thing, its freezing point is 0 degrees Celsius. Since water expands as it freezes, a cold winter night could mean a cracked radiator and a damaged engine block, a chilling prospect. And considering how hot car engines can get, the relatively low boiling point of 100 degrees Celsius can lead to a situation that would get anyone steamed. So instead of water, we use a solution, a homogeneous mixture consisting of a solute and a solvent. Some of a solution's properties will differ depending on the proportion of solute present. These are called colligative properties, and as luck would have it, they include freezing point depression and boiling point elevation. So solutions have both a lower freezing point and a higher boiling point than pure solvent. And the more solute is present, the bigger the difference. So why do these properties change? First of all, we need to understand that temperature is a measure of the particle's average kinetic energy. The colder the liquid, the less of this energy there is, and the slower the molecules move. When a liquid freezes, the molecules slow down enough for their attractive forces to act on each other, arranging themselves into a crystal structure. But the presence of solute particles gets in the way of these attractions, requiring a solution to be cooled down further before the arrangement can occur. As for the boiling point, when a liquid boils, it produces bubbles filled with its vapor. But for a bubble to form, the vapor pressure must become as strong as the atmosphere constantly pushing down on the surface of the liquid. As the liquid is heated, the vapor pressure increases, and when it becomes equal to the atmospheric pressure, the bubbles form and boiling occurs. A solution's vapor pressure is lower than that of pure solvent, so it must be heated to an even higher temperature before it can match the strength of the atmosphere. As an added bonus, the pressure in the radiator is kept above atmospheric pressure, raising the boiling point by another 25 degrees Celsius. The solution commonly used for a car's cooling system is a 50-50 mixture of ethylene glycol and water, which freezes at negative 37 degrees Celsius and boils at 106 degrees Celsius. At the highest recommended proportion of 70 to 30, the freezing point is even lower, at negative 55 degrees Celsius, and the boiling point rises to 113 degrees Celsius. As you can see, the more ethylene glycol you add, the more protection you get. So why not go even higher? Well, it turns out you can have too much of a good thing, because at higher proportions, the freezing point actually starts to go back up. The properties of the solution head towards the properties of ethylene glycol, which freezes at negative 12.9 degrees Celsius, a higher temperature than we attained with the solution. The solution flows through the engine, absorbing heat along the way. When it reaches the radiator, it's cooled by a fan, as well as air rushing through the front of the car before returning to the hot engine compartment. So an effective and safe engine coolant must have a high specific heat, a low freezing point, and a high boiling point. But instead of searching all over the world for the perfect liquid to solve our problem, we can create our own solution.